Chapter 12, Statistics. Section 12.1 is Sampling, Frequency Distributions, and Graphs. The objectives: describe the population whose properties are to be analyzed, select an appropriate sampling technique, organize and present data, identify deceptions and visual displays of data. Statistics is a method of collecting, organizing, analyzing, and interpreting data, as well as drawing conclusions based on the data. The methodology is divided into two main areas. You have descriptive statistics, which is the collecting, organizing, summarizing, and presenting of data, and the inferential statistics, which is making generalizations about and drawing conclusions from the data collected. A population is the set containing all the people or objects whose properties are to be described and analyzed by the data collector. A sample is a subset or a subgroup of the population. A representative sample is a sample that exhibits characteristics typical of those possessed by the target population. Example 1, populations and samples. A group of hotel owners in a large city decide to conduct a survey among citizens of the city to discover their opinions about casino gambling. A, describe the population. Solution. The population would be the set of all citizens of the city. B, one of the hotel owners suggests obtaining a sample by surveying all the people at 6 of the largest nightclubs in the city on a Saturday night. Each person will be asked to express his or her opinion on casino gambling. Does this seem like a good idea? Solution. Questioning people at 6 of the city's largest nightclubs is a terrible idea. The nightclub subset is probably more likely to have a positive attitude toward casino gambling than the population of the city's citizens. Therefore, it wouldn't represent the city population itself. A random sample is a sample obtained in such a way that every element in the population has an equal chance of being selected for the sample. The methodology is identify each element in the population, assign numbers to each element in the population, randomly select numbers, and assign the elements in the population who have those numbers to the sample set. Example 2, selecting an appropriate sampling technique. Which of the following is the best way to select a random sample to find out how the city's citizens feel about casino gambling? A, randomly select people or randomly survey people who live in the oceanfront condominiums in the city. The response is, many hotels lie along the oceanfront, and these people might object to the increased traffic and noise which may result. It also does not give each citizen of the city an equal chance. For B, survey the first 200 people whose names appear in the city's telephone directory. Again, this does not give each citizen in the city an equal chance. C, randomly select neighborhoods of the city and then randomly select people within the selected neighborhoods. This would be appropriate because it gives each citizen in the city an equal chance. Example 3, constructing a frequency distribution. We want to construct a frequency distribution for the data of the age of maximum yearly growth for 35 boys. So we have the numbers for them. We first want to put them in a table. So we have the age of maximum growth. we see that looking at the numbers on the left, the smallest number is 10 and the largest number is 18. So we're going to list 10 through 18. For the next column, we want the number of boys, which would be the frequency. So we're going to list each time that age occurs. For age 10, it occurs only once. For age 11, it occurs twice. For age 12, it occurs 5 times, and so on. And we need to make sure that our frequency totals to be the number of people that we're looking at, which is 35. What are some conclusions we can draw from this sample? Well, looking back at the table, we can see that the maximum growth for most students or most subjects occurred between the ages of 12 and 15. It's less before 12 and it's less after 15. The number of boys who attain their maximum yearly growth at a given age increases until age 14, and then it decreases after that. So you can determine all this from the table that we came up with. Example 4. Here are the statistics test scores for a class of 40 students. We want to group the frequencies into classes that are meaningful for the data. Since letter grades are given based on 10-point ranges, we're going to use the classes 40 to 49, 50 to 59, 60 to 69, 70 to 79, 80 to 89, and 90 to 99. We then take the numbers that we were given and we put them into our table. We have listed the classes and then the frequency for each of the classes. The frequency for the class 40 to 49 is 3. The frequency for the class 50 to 59 is 6, and so on. The class 40 through 49 has 40 as the lower class limit and has 49 as the upper class limit. The class width is 10. Sometimes it's helpful to vary the width of the first or last class to allow for items that may fall above or below most data. Notice in the table that when we add the frequencies, they have to total the number of things that we are looking at. In this case, 40. Next, histograms and frequency polygons. A histogram is a bar graph with bars that touch, and it can be used to visually display the data. Frequency polygon is formed by connecting the dots in the midpoint of each bar of the histogram. So we've taken the top of each bar in the middle and we connect the points to form a line graph. Stem and leaf plots. This plot is constructed by separating each data item into 2 parts. The stem might consist of the tens digit and the leaf would consist of the units digit. Therefore, in example 5, constructing a stem and leaf plot, we're going to use the data below for a stem and leaf plot. You examine the numbers, always try to find the lowest one and the highest one, and see if there are ranges or anything we want to work with. Okay, we're going to enter the data items in the first row. We have 4 and 7, 5 and 7, 6 and 4 and 3, 7 is 5, 8 is 22, and 9 is 3. Going back to our numbers here. We're going to continue with the remaining rows. Now, remember that for this table, the tens digit is the stem, So we've got 47, 45, 43. These are given in our numbers. Then we have 57, 54, 56, 57, 50, which is the 5 and 0, and 59, and so on. On this slide, we're going to consider deceptions in visual displays of data. Graphs can be used to distort the underlying data. The graph on the left stretches the scale on the vertical axis to create an impression of a rapidly increasing poverty rate. So you can see that we've got the vertical scale going up is 11.3, 11.7, 12.1, 12.5, 12.9. So there's 0.4 between each of these. So it makes it look like it's increasing much more than if you had a smaller distance between each of the lines going across. The graph on the right compresses the scale because we see that the lowest number is 11.7, so we can use 11, 13, 15, 17, 19. That's what we can use for the vertical axis, and that gives us a better representation of the data. Here are some hints, things to watch for in visual displays of data. You might see this in newspapers, on television, in various places. Is there a title that explains what is being displayed? Are the numbers lined up with tick marks on the vertical axis that clearly indicate the scale? Has the scale been varied to create a more or less dynamic or dramatic impression than shown by the actual data? Do too many design and cosmetic effects draw attention from or distort the data? Basically, is the graph too pretty? Are there a bunch of things there that don't really have to be there? Has the wrong impression been created about how the data are changing because the equally spaced time intervals are not used on the horizontal axis? Furthermore, has a time interval been chosen that allows the data to be interpreted in various ways? Continuing, are bar sizes scaled proportionally in terms of the data they represent? And finally, is there a source that indicates where the data in the display is coming from? Does the data come from an entire population or a sample? Was a random sample used? And if it was, are there possible differences between what is displayed in the graph and what is occurring in the entire population? Who is presenting the visual display, and do they have a special case to make for or against the trend that is shown in the graph? And we're going to end with some examples of misleading visual displays. Cosmetic effects of homes with equal heights with different frontal additions and shadow lengths make it impossible to tell if they proportionally depict the given areas. Time intervals on the horizontal axis are not uniform in size, making it appear that dwelling swelling has been linear from 1980 through 2010. The data indicate that this is not the case. There was a greater increase in area from 1980 through 1990, averaging 34 square feet per year, then from 1990 through 2010, averaging approximately 15.6 square feet per year. So here we are visually misleading the person who is looking at the display. And this concludes this lesson.